Hello, dear students. Let's learn the conversion of the linear programming problem or the mathematical problem into the dual form, and from that we will be solving into the graphical method. So first we need to see that whether this mathematical model in the canonical form or not. First step is to check the canonical form. So this is the basic model which has just been derived from the problem, the real problem. From the real problem, we have just come up with this linear programming model or linear programming problem or the mathematical model we have. So we need to see whether it is in the canonical form or not. So how do we see it? In the maximization function, objective function, the inequalities must be less than. Inequalities must be less than. So you see both inequalities are already in the less than. So it is in the canonical form. Let's move ahead. Now, we know in the dual form, the objective function will be converted into the minimization one. Okay, and the values would be z equals to, we don't take it z anymore, we take it w instead z, so that it is different. Basically, duality is the another form of the linear programming model. So just to find the optimum solution in other way, so we try to convert the basic model into the dual form and solve it. So it is another way to check your solution. So you see, in the minimization, we have to convert the maximum into the minimum one. It is converted, w is there instead of z, it is w instead of maximum function, it is minimum function. You see, so instead of 3, that is the coefficient of the objective function, we will be using the 8, the first value of the first objective function, the first constraint, the second constraint. So the first right hand side of the first constraint of the right hand side, that is 8. So we will write 8 over here, and x1 will be same, the variable will be same. Second is the right hand side, second constraint you see is this, and its right hand side is 5, plus 5. So we will write plus 5. The variable would be same. So this is the minimization function in the dual form. Now let's find out the constraint as well. So for the constraint, what you do, you just develop a matrix from the constraints coefficients. The first constraint coefficient is 2 and 3. Okay. Second constraint coefficient is 1 and 2. So we have to transpose it. So transposed would be, matrix would be, it convert, you have a choice, either you convert the row into column or column into row. Okay, so it is your choice. So let's take the row into column, that would be 2, 3, and 1, 2. Okay, so these are the new coefficients of the constraints of the dual function, duality. So the constraint would be, first coefficient of the constraint would be 2, and x1 variable would be same, plus 1, we don't write 1, x2. Okay, since it is the minimization function, so in the minimization we take the greater than sign instead of the less than sign, and instead of 8 we will be using the coefficient of the objective function, that is 3. Okay, so let me reiterate. 2 is the transposed matrix we found. Okay, and x is the variable, plus 1 is the next coefficient with the variable x2. Since it is a minimization, we have the objective of minimization, so the inequality would be greater instead of less than. With the right hand side, we have to change the right hand side from the objective function x1 coefficient, that is 3. x1 is the first coefficient, x1 is the first variable, and first variable coefficient is 3. So next, what would we do? The next is 3, and the variable we know is 1, x1, plus next is 2, next variable is 2, x2, and the inequality would be greater than n equals 2, and you see 5 is the next coefficient of objective function, so we will take the 5. Now we have come up with the minimization objective function, you see, and these are the constraints, the first constraint and the second constraint. So you see the first constraint is transformed from 2x1 plus 3x2 to x1 plus x2 mein, and the inequality is changed from the less than to the greater than equals to, and the right hand side is changed from 8 to 3. And the second inequality you see from the x1 plus 2x2 is changed into 3x1 plus 2x2. The less than inequality is changed to greater than, and 5 is changed into 5. 5 is same. So you see, these are the new one. The objective function is quite changed from the 3x1 plus 5x2 to 8x1 plus 5x2. So we are done with this. But remember to write, very importantly, the variable, we cannot use x1 and x2. We cannot use x1 and x2 as a variable in the dual form. So what we can do y, or you can choose any other variable, y. Y has to be used, y. Okay, so remember that. So at the end you write y1 comma y2 greater than equals to 0. So we are done with the dual form. Now, as the problem is, solve the problem by the graphical method. First we had to change in the dual form, then we have to go for the graphical method. So let's move ahead for the graphical method. So our minimization function is, let's rewrite again. Instead of z, we write w. 8y1 plus 5y2 y2, 2 y1 plus y2 greater than equals to 3. 3 y1 plus 2 y2 greater than equals to 5. So this is the mathematical model which is in the dual form. So we have to solve it through the graphical method. Let's begin. So in the what is graphical method? We find the extreme points through it. So for the extreme points, you need to find out the x-intercept, you have to find out the y-intercept, you have to find out different points through which you can make the line. So this is the equation we have. So 2y1 plus y2 equals to 3. 3y1 plus 2y2 equals to 5. So you see, we have two equations. We have changed this inequalities into the equal form. So you see, these are the two equations we have. So why we have changed? Because so that we can find the x-intercept and y-intercept of these equation. So let's find the equation 1. Let's find the x and y-intercept. For that, y1, y2, y1 equals to 0, y2 equals to 0. This we had to make so that we don't miss any point. So we will be finding this point and that point. So this will be the y1 intercept, this will be the y2 intercept. Okay, so let's begin with the 2y1. In which y1 is 0. So when y1 is 0, 2 in equation 1, 2, 0 plus y2 equals to 3. Okay, so 0 into 2, 0 plus y2 equals to 3. So y2 would be 3. It would be 3. So this is the first point we have found of this equation. For the second point, what we do, we have to put y2 equals to 0, y2 equals to 0 in the equation 1. So 2y1 plus 0 equals to 3, and 2y1 equals to 3, and y1 equals to 3 by 2. Or you may write 1.5. Okay, so y1 would be 1.5. Now we have found this line would be made because there are 2 points. So we will make a graph, and from the graph we will make first point 0, 3, second point would be 1.5 or 0. Okay, let's move ahead with the equation 2. So in the equation 2, we will be doing the same. Okay. Equation 2 is y1 equals to 0. So 0 plus 2y2 equals to 5. So you see, instead of y1, we wrote 0. Okay, 3 into 0, that is 0, plus 2y2 equals to 5. Then y2 would be 5 by 2. We will divide 2 on both sides. Okay, so 5 by 2 is 2.5. It is 2.5. Now, when here you see y1 equals to 0, now we are going for the y2 equals to 0. This is the y2 intercept. The y2 intercept we will put in the equation number 2. Okay, 3y1 plus 2 into 0 to 5. So you see in equation number 2, if you put y equals to 2, y2 equals to 0, y2 equals to 0, so the equation would be like this. 3y1 plus 0 equals to 5, and y1 equals to 5 by 3. What does that mean? We divide 3 on both sides. So 1.67, 1.67. Let's move ahead. So we have found this. Now we can draw, and after drawing that, we will find the intersecting point through equating the equation. Through elimination method, we'll eliminate and find the intersecting point. Okay. So we have a choice: either we find the intersection point first, but we will go to draw first, so that, because there is a possibility that both lines are not intersecting. There is a possibility, because the mathematical model can be like that. Okay, let's draw this. Okay. Now you see what we have to draw: maximum 3, up till 3 or something. So this 1, this 2, this 3, likewise 1. With the approximation, obviously we don't have a graph, so with the approximation we are going towards it. Okay, so we are done with this. So what are the points we had? So let's write all the points so that we don't miss any. We have y1 comma y2, y1 comma y2, y1 comma y2, y1 comma y2. So with the equation 1 we got the equation 1, we got this equation 2, we got, so these were the points, just to make you remember about it. Since we have not given any symbol for it, so you see equation 1, 0, 3, 1.5, 0, 0, 2.5, 1.67, 0. Okay. So these were the points we found. So just to recall, okay. So I have mentioned all the points over here so that it will be easy for you to recall and we don't miss anything. Now we have to draw it 0, 3, 0, 3. This is y1, this is y2. Okay, so y1 is 0 and y1 is 0 and y2 is 3. It is there. y2 is 3. Another one is y1 is 1.5. It must be here. And y2 is 0. So it must be here. So we need to draw it. Well, let's draw it. Okay. Now the another points would be 0, y1 is 0, y1 is 0, and y2 is 2.5. So it must be around here. Okay. It is approximation, obviously. It is not a definite one. So next point would be y1 is 1.67, y1 is 1.67, y2 is 0. So we will take it over here. Okay, so we have to connect both lines together. So you see both lines are connected now. We need to see in our problem that they were the greater than. They were the greater than. So they must be greater than. Greater than sign will be opposite to this from here. It will be opposite. Okay, so you see over here, the arrow would be this is this, arrow would be here. Okay, and if you see this line, arrow would be upside. Okay, so this is, so which one is the common region, common feasible area? Okay, let's see it. Why? Because it is greater than. So because of greater than, it is outwards. It is not inwards. If it would be lesser than that, they will be inwards. So we have made it the outwards. So you see which one is the common one. Is this the common one? No. Is this the common one? No. So this one is the common one. This one is the common one. And what are the points we had over here? This one, A, B, C, A, B, C. So three extreme points we have on this on this common area, or the feasible region we have. Okay, so let's find the intersection point, that is B over here, as I already mentioned B. So for B, finding intersection point or finding intersection point B, what we will do, we will equate the equations, both equations what we made over here. You see, we'll equate them. How would we equate them? We have to eliminate. We have to use the elimination method. And in the elimination method, what we do, we try to make them equal. For example, we need to eliminate the y2. So for eliminating the y2, we need to make the y2 same, so that we can subtract and eliminate. So first we would multiply 2 by equation 1. Okay, multiply 2 by equation 1. So the equation 1 would be 4y1 plus 2y2 equals to 6. 2 to the 4, 2, 1 the 2, and 2 to the 6. So equation 1 has become this one. Now, the previous equation 2 was, which we did not do anything with that. Now we have to subtract and eliminate. So subtract this from this. Subtract this from this. What will happen? 6 minus 5, 1. This is plus 2y minus 2y, 0. Plus 4y minus 3y, 1. Plus 4y1 minus 3y1. It would become plus y1. So y1 equals to 1. Now we have found the y1 value. We must go for the y2. So for the y2, we have to put this y1 value into the equation number 1 again. 2 1 plus y2 equals to 3. What we did, we put the y1 value, that is equals to 1, into the equation number 1. 2y1 plus y2 equals to 3. 2 plus y2 equals to 3. So y2 became minus 2 on both sides. It became 1. So what we found, the third point is, we found 1, 1. So another point was, that is the intersection point, that is point B. Or we may rewrite the point A, point B. First we write point B is 1, 1. The point A was 0, 1 point. Point A was 1.67, 0. Okay, point A was 1.67, 0. This is that. And point C was 0, 3. So these are the 3 points which are the extreme points. On that we have to find the objective function. So we already know the objective function, that is W equals to 8y1 plus 5y2. Okay, now we will be finding the extreme point, that is A 1.67, 0, B 1, 1, C 0, 3. Now put these values in the equation, these values of y1 and y2 in the equation. So you see 8 into 1.67 plus 5 into 0 would be, you may use calculator for that. So 8 into 1.67, 8 into 1.67 is 13.36. 13.36. 5 into 0 is 0, so we don't write it. Next is, we have 8 into 1 plus 5 into 1. So you see, we are putting the y1 into y1, y2 into y2. So 8 plus 5 is 13. And next is c. So we put into the objective function 8 into y1 is 0 and y2 is 3. 5 3 is 15. 8 into 0 0. 15 is there. So you see, we have found the extreme points of this dual function, dual minimization problem. So you see, since it was the minimization problem, so in the minimization problem we have to select the least value, that is 13. That is 13. So 13 is the least value. So you see, the optimum value of z, when z may be the cost would be minimized when the y1 equals to 1 and y2 equals to 1. Okay, so z will have the least value, that is 13. Thank you very much.